third session of this wonderful meeting. And I'm happy to welcome as the first speaker of our morning session, Peter Knowles from Cardiff University. And he's going to talk about multi-configurational methods for excited states. So I'm very much looking forward to your talk, Peter.
Thank you very much, Stefan, for the introduction, and thank you to Christian, David, and others who were kind enough to invite me to come on to this great meeting. I was asked to speak a little bit about multi-reference methods, which I'll do, and I'm going to actually give a little bit of an overview, not too much, because I think that's been done by other speakers and will be done by other speakers, and talk a little bit about some of the technology that we've developed over the last years to help with that. And in the second bit of the talk, I'm going to move on from there to talk about some more recent work where we've tried to look at doing quantum calculations that include both electrons and bosons, either vibrations or photons. So that's the plan. Okay, so let's first of all summarize what we mean by multi-configurational reference methods. These are to be used when we don't like the idea of using Hartree-Fock as our first starting point. And our reason for that might be already that in the ground state, there is some strong correlation. So the Hartree-Fock is a very poor starting point. Or we might be interested in an excited state, which is unlikely to be described by Hartree-Fock. So what do we do? Well, in the multi-configurational approach, we choose as our first wave function, our zeroth order wave function, which is already a linear combination of stated determinants. And the idea is that those slated determinants contain everything that's somehow important, maybe covering all of the relevant electronic states, covering dissociation products, and so on and so on. And we all know that the way to do that successfully is to, instead of defining a set of configurations, define a set of orbitals, and then choose all configurations within that orbital space. Or you can do some of the things that Laura spoke about yesterday to truncate that space. Typically, the MCSCF or CASSCF calculation does not give us the quantitative accuracy that we need for a typical application. It misses out the contributions from dynamic electron correlation, and the way that we can recover those systematically is to think of the MCSCF as a zeroth order wave function for perturbation theory, and then look at the states that would come in the first order wave function. So there is could be the first order wave function, or it could be anything you like. It's a linear combination in the first order interacting space of that MCSCF wave function. EPQ and ERS are operators that excite from one orbital to another. And the idea is that you do those excitations on the whole MCSCF wave function. So each of those so-called contracted configurations is itself a mixture of many slated determinants because of the many determinant nature of the reference wave function. What can we do with that? We can do a variational calculation. That's configuration interaction, multi-reference configuration interaction. We can try to correct for the effects of the lack of extensivity of that variational approach, either do coupled cluster theory or some approximation to it, or we can address both the extensivity and actually the high cost of multi-reference configuration interaction by doing second order perturbation theory. So this is a well-established method. It's accurate, general, but it's expensive and typically has poor scaling. And we have to be aware that in non-variational approaches, we may have trouble with intruder states and other complications. So I want to talk with some embarrassment about the problem that was given to me by my PhD supervisor on day one. And it's embarrassing because it was so long ago, but it's actually something we've picked up recently: how to actually solve the MCSCF equations. It looks very simple. There is the wave function. It's a linear combination of these determinants, and those determinants are products, anti-symmetrized products of orbitals, and those orbitals are linear combinations of some fixed basis set. And the problem is simply to minimize the expectation value of the energy. It could be the energy of a single state, or it could be the average of several states if you want to look at excited states, to minimize that with respect to the coefficients of this kind of configuration mixing and the molecular orbital coefficients. I've missed out the complication of constraints. And we hit some challenges when we do that. If we want to apply this to chemically interesting molecules, we have to keep an eye on cost. And it turns out there are some expensive matrix transformations you have to do, chiefly associated with bringing the Hamiltonian from this so-called atomic orbital basis set into the molecular orbital basis set. But there are other challenges as well. It's not so easy to converge to the minimum energy, and not necessarily easy to converge to the global minimum of that energy. There may be multiple minima. The typical thing you might think of doing is to make some small polynomial approximation to that energy functional and use that. I'll talk about that in a moment. But typically those approaches are plagued by a small radius of convergence. So you can't get very far towards the minimum in each iteration that you take, or you may step to the wrong place. The other thing that's going on, again, this is touching base with last night's session, you may want to do this with a very large CI expansion using some of the exciting techniques that have been developed over recent years to do very large full CI expansions. And that has to factor into your considerations of how to do this and actually finish the calculation. And the other thing that's going on is that the changes in orbitals are strongly coupled typically to changes in the CI coefficients. So you have some maybe near linear dependencies in the optimization parameter space. Okay, I'm going to talk mostly about the orbital optimization problem. You have to be aware that at the same time we are optimizing the CI coefficients, and I don't want to spend a lot of time in talking about the detail of how that's done. But let's just look at this and think about what you have to do. The natural thing to do is to make a polynomial expansion in a parameterization of the orbitals. And because we want those orbitals to be orthonormal, then we probably want to do this by making a unitary transformation. We could do it with Lagrange multipliers, but the approach that's usually used is to make an explicitly unconstrained unitary transformation, which we can set up using the infinitesimal generators of rotations, which are actually these operators here, where these E's are again orbital excitation operators. So we can take the exponential of that antisymmetric matrix, antisymmetric operator, anti-emission operator, and that will generate a unitary rotation of the wave function. And then all we have to do is expand the rotated Hamiltonian in powers of the parameters R, where R somehow takes us from the place where we are to the next iterate. And that's pretty easy to do using commutator expansion. And that means in turn that we get a power series expansion for the energy, which we could truncate at second order. And then we can just minimize that quadratic form, or perhaps more cleverly use the augmented Hessian matrix, where lambda is some damping parameter in order not to suffer from the problem that might occur if the Hessian matrix has got negative or small eigenvalues. And that will give us solution of those linear equations, or linear eigenvalue problem will give us the step to the next point, which we hope is closer to the solution. Actually, we found a long time ago that it's better to reparameterize at this point in a nonlinear way. And instead of using the parameters, which are the infinitesimal generators, actually use the changes in the orbitals themselves. In other words, the difference between the unitary rotation matrix and the identity, and make a second order expansion of that. That becomes a nonlinear optimization problem because you have to optimize that with respect to R, so you have to do that iteratively. But it turns out this is not too much more complicated than solving the linear equations, given that both have to be done iteratively anyway. Okay, in order to do this, to construct these Hessian and gradient matrices, you need molecular orbital integrals, and it turns out that you need them with two indices belonging to either the active space or, importantly, the closed shell orbital space. So if we think about a large molecule, then there'll actually be very many more closed shell orbitals than active orbitals. And this is the difficulty, actually, with this second order approach. The convergence is very robust, but it's very expensive when you have a large molecule with a large number of closed shell orbitals. So that's a second order approach. Now, if you want to avoid this, you can drop back to an approach where you evaluate only the gradient vector, not the Hessian matrix. And that will be we call that a first order optimization method. Again, this is a very old technique, the so-called super CI method, where you make a wave function which consists of the CASSCF wave function plus single excitations generated by these operators. And then we just approximate the Hamiltonian matrix between those single excitations, but importantly not between the current MCSCF wave function and those excitations. And then you can just diagonalize that, or find the lowest eigenvalue of that matrix in order to get the parameters R that hopefully get you close to the solution. And the big advantage of that is it requires integrals with just one of the indices belonging only to the active space, and that makes a huge difference in terms of what you have to compute. Okay, the work we've done recently is to bring those two together. So to be able to do quite large molecules, but still get the benefit of the second order optimization. I'll show you in a moment an example where you need it. So actually you'll find in Molcus already since many years that the first order method is not really a first order method because they use a quasi-Newton accelerator around that. The BFGS method works by taking the history of parameters and gradients and building on the fly the effects of an inverse Hessian matrix by essentially numerical differentiation. Okay, let's think about how we could exploit that in a smart way. What's going on with the BFGS method is that the thing that it requires a user to give is an approximation to the inverse Hessian, which it then refines using the history. In the low memory variant of BFGS, then you never actually store that Hessian, and you simply construct the action of the inverse Hessian on the fly, the action of the inverse Hessian on the gradient in order to do Newton-Raphson step. And in the middle of that procedure, the user is expected to provide something which is essentially a preconditioner that would take a gradient vector and give the best possible step in the parameter space. So this is related to, for example, the Davidson diagonalization method, where the preconditioner is just division of the gradient by diagonal elements of the Hamiltonian matrix. It's the same thing. And so normally you would choose that approximate Hessian at the very start of your calculation and just leave it alone, but it's possible to do better. So what we do is to think of the optimization as an optimization of the closed shell orbitals, and they are done using first order method and using BFGS. But the preconditioner is actually the rest of the program that does the second order algorithm for the active orbital and the CI optimization. Okay, so that preconditioner, which in a Hartree-Fock calculation would be diagonalization of the Fock matrix, that now is replaced by most of the algorithm that you would use, the entire second order algorithm, but not including the closed shell orbitals. So this means that we can get away without calculating the very large number of integrals that we would otherwise have to, but yet get the benefits of the strong convergence, both reliability and rate of convergence that you get with the second order algorithm. Let's just look at how it works. Here's an example, a dicobalt complex. This is doing a relatively modest CASSCF, but we've done larger and with larger basis sets. And this just compares how the energy converges towards the final solution using either the super CI method on its own, pure first order method, together with BFGS, and that's the orange curve, or using the second order approach for the preconditioner, which is the blue curve there. And essentially we get there in much faster, and we can converge hard to as many decimal places as you want. So there are other examples where actually the first order approach may fail to reach convergence, or you don't even know quite, because the speed of convergence is so slow, whether or not you've reached there. And in those cases, we still get success with this approach. Right, so that is a little bit on the technology. What would we want to do with it? Oh, I just wanted to say something about this. This is a small advert for actually part of the methodology that we use, having re-implemented things like DIAS and Davidson and so on, BFGS, numerous times in different kinds of equation systems. We got fed up and decided to write a proper implementation that allows you to include some of the numerical subtleties that you really need to get robust convergence. So we now have this open library, which has got two parts to it. One is a set of containers, which are essentially objects, classes which can contain large data structures. And there are various different ways of implementing this, which all have the same interface. Either they can be in memory distributed with MPI3, or they can be, if you really want, on HEF5 files, or on disk files, distributed MPI, or global arrays, or even just simple data. And the thing that goes with this is that the basic linear algebra operations are implemented for those classes. So scalar product and in general matrix multiplications, together with some other what we call handlers, which implement those operations between pairs of container classes. And this goes to help the other side of the library, which is a thing which will solve numerical problems iteratively for these four classes of problems. Actually, they're in two pairs: linear methods for either the eigensystem or inhomogeneous linear equations. So that's basically the Davidson method, or nonlinear equations, that's DIAS, or related to it is minimization with LBFGS. And the key thing is that this bit of the software knows nothing at all about the data. The only thing it uses are these operations. And you can use this part either with these containers or your own class. Of course, there's a Fortran interface to this, which just uses flat real star rate arrays. So if you're interested, we'd be very interested to talk to you, actually, if you have an application where you'd like to use this, and we'd be interested to see how well it works for you. Okay, having got such methodology in place, what can we do with it? Here's an example of doing dynamics on a typical photochemical problem. This is the photochemical ring opening of cyclohexadiene. This has been done actually with relatively modest CASSCF with CASPT2, and then using surface hopping for the dynamics. And that's sufficient to build up a story of the mechanism of the photodissociation, which actually involves excitation to the bright state, and then passing through two different conical intersections. One where you transfer onto this dark excited state, and then this has a conical intersection with the ground state, and you can either go to products or back to reactants. Okay, I haven't got time to talk about a lot of that, but other than that, but except to point forward to the rest of the talk. One of the problems, two problems really, with this way of doing photochemistry, excited state dynamics. One is it's pretty difficult to do quantum calculations. It's possible, but it's pretty difficult. And in this, we did semi-classical calculations. It'd be nice to do full quantum mechanics. And the second is, though, you then using trajectories and have to calculate really very many points on the potential energy surface in order to get sufficient statistical sampling of the trajectories. It'd be nice to avoid that. So I'm now going to try and talk about another way of doing non-adiabatic dynamics, of coupling the motion of electrons and the motion of nuclei. It's almost always the case that in photochemistry and maybe spectroscopy too, that you hit an electronically excited state which has a conical intersection with another electronically excited state, and that conical intersection makes a difference to the photoabsorption spectrum, makes a difference to the branching to products. So let's just review the standard approach, which is Born-Huang. Basically, we've got a Hamiltonian, which is the electronic Hamiltonian, plus the nuclear kinetic energy operator. And we're thinking about nuclear coordinates, which are labeled with X, and electronic coordinates which are labeled with a little x. So the first thing we do, as we all know, we solve the electronic Schrödinger equation for a given value of capital X, the nuclear positions, and then we use the eigenvalue as a potential, effective potential in the nuclear motion Schrödinger equation, which we can do coupling the states. So we have the nuclear kinetic energy operator there, and we have to worry about the action of that nuclear kinetic energy operator on the eigenvalues of the electronic problem, because it doesn't go away. The Born-Oppenheimer approximation, of course, we would ignore that. If you read a theory textbook, then you might be tempted to do the expansion of the wave function of the diabatic states, which are the electronic eigenvalues at a fixed value of the nuclear positions. But this is completely hopeless in practical applications, because you would need far too many states. Okay, now here is the aspiration of what we're trying to do, and it's actually related to how to, well, really the very many applications which do non-adiabatic dynamics, particularly in condensed phases, but also using model Hamiltonians for molecules too, where we would want to just set up some simple simplified approach where we have the electronic Hamiltonian, we have a model Hamiltonian for the nuclear motion, which I've just written as harmonic oscillators, and then something, the rest of the Hamiltonian, which I've written exactly there, but then that interaction you might try and expand and make an approximation. So this is actually just a linear approximation, a first order approximation, first order in displacements from a reference geometry. And that would mean that we have to just evaluate these so-called non-adiabatic coupling, the derivative of the Hamiltonian with respect to nuclear positions, only at this reference geometry. And this is kind of the underpinning of semi-empirical models, but it doesn't immediately lead us to have an ab initio treatment. Okay, and it's complicated because we already have a lot of the nuclear electronic correlation, of course, in atomic orbital basis calculations, because the basis functions move with the nuclei. Okay, so let's now think about how we could set up second quantization for vibrations and photons, if you like. So the normal way that you would think of doing this, you would realize that we're talking about bosons. We need to use boson creation operators to generate a set of states. But this is okay, this can be done, but it's a bit inconvenient. If you come from the electronic structure world, you want to reach for configuration interaction, you want to reach for coupled cluster theory, where what you would want is excitation operators that are nilpotent. You apply them once, and then the second time you apply them, they just annihilate. So another way to go is the approach which was first put out, I think, by Ove Christensen, which is instead to use excitation operators, where we generate the 1, 2, 3 boson states by exciting in some fictitious space from the ground state to one of the excited states. So you can see that on this ladder of states. These are the harmonic oscillator basis functions, and these operators Tor just take you from the bottom here up to any of the excited states. You can imagine this as a one particle system with a Fermi level above that first one particle state. And then those excitation operators have the same properties as electronic excitation operators. They're not really bosons, they're not really electrons. Actually, it doesn't matter because there's only ever one of them. So you can use fermionic algebra with these things. And in fact, this is exactly what we do in work we're doing now that I'm not going to talk about. Then all we have to do actually is change the Hamiltonian. You can think of this if you've got electrons plus, let's say, a molecule in a cavity. You've now got 3 kinds of electrons: alpha spin, beta spin, and cavity excitations, or alpha spin, beta spin, normal mode 1, normal mode 2. And it's just really the same as electronic. Once you set up the Hamiltonian, then you can use the same program to do coupled cluster or whatever you want to do. Okay, here's a first go at using that formalism, which is to look at electrons in a cavity. So this time the Hamiltonian contains the electronic Hamiltonian plus some parts which have got annihilation and creation operators in this cavity, which has a natural frequency omega c. And what you can then do is to look for the photoabsorption cross-section as a function both of the incoming photon and the cavity frequency. This is done for just a simple model of a four-side Hubbard chain in a reasonably strong coupling through this parameter gamma. And let's just see what we're looking at. Here is the electron-only full CI calculation. So you see the electronic eigenvalues there are maxima in the photoabsorption cross-section. Here is the same thing using CCSD for just the electrons. And then to the right, we're bringing in the photons. So on the far right is actually full CI involving the electrons and the cavity mode. And you see some diagonal lines of unit slope. Those are basically just the cavity modes, okay, resonance between the photon energy and the cavity. And the interesting stuff happens when they cross the electronic eigenvalues. And these are different couple cluster ansatzes, basically the excitation level of the electronic only part, the bosonic part, and the coupling between them. And you can see that if you include enough excitations, then you basically reproduce the full CI spectrum. Okay, I think I should move on. Let's just now think about what we would need to do if we need to move to vibrations. Think about the additional complications that have come in. In principle, it's all the same, but we have the additional complication that, of course, the electronic wave function is already tied to the nuclear positions. So let's just set up the formalism a little bit. We're going to have a basis set, which is a product of electronic functions, stated determinants, which also depend on nuclear position, and then nuclear functions, which depend on the nuclear position. And the orbitals vary with nuclear position, but otherwise there's some free choice within an orthogonal transformation. And in the Hamiltonian, the matrix elements between these states, we're going to have the electronic Hamiltonian, the nuclear kinetic energy operator just acting on these nuclear states, but also coupling, which is the operator acting on both the electronic and the nuclear state. And that coupling, you can perhaps recognize the normal non-adiabatic coupling vector plus the bit that's essentially involved with the diagonal Born-Oppenheimer approximation. Okay, so my time is hopelessly running out, and I want to just show you a couple of things you can do with this. The first way we've done this is to do full CI. And you can do that if you've got a small enough number of electrons. Here's an example where there is some non-adiabatic coupling, that's dicarbon. If you look at the potential energy curves, then there's a near crossing between the X and the B states. And we have to then calculate these matrix elements of the non-adiabatic coupling. And we do a calculation where the basis set is the outer product of the electronic full CI and a set of vibrational basis functions. And we do this calculation essentially exactly. I guess I haven't got time to talk about those numbers, but what you can do with them is you can actually then look at the reduced density matrix to see whether there really is some correlation between the electrons and the nuclear motion. Either by, you can project them onto the Born-Oppenheimer states, or perhaps more elegantly, construct the reduced density matrix, whose eigenvalues, if there were no correlation, would be 1 and 0. But if there is correlation, then it's between 0 and 1. And I'm sorry for all the numbers, but perhaps down here you can see that there are some eigenvalues of the Vibronic states, which are between 0 and 1, strong coupling. And then for some regions, it comes back to uncoupled. And of course, we're just passing through resonances between ground state, vibrationally excited, and excited state, electronically excited state, vibrational, less excited. I want to skip those details. In order to do practical calculations, then we need to simplify somewhat. And a simplification essentially is looking for an approximate Hamiltonian, which is at most two-body. And it looks something like the bottom of the slide there. By making some approximations, you essentially have a one-electron operator, and together with just displacements in the nuclear coordinates, and then these terms are just including the non-adiabatic coupling vector at a reference geometry, that's this little pi here, outer product with the derivative with respect to the nuclear coordinate acting on the vibrational basis. This is just a showing the, thank you, Stefan, I'm aware of the time. This is just showing how the potential energy surface using that model Hamiltonian compares with the potential energy surface that you would just calculate pointwise, and the basic along a number of different normal coordinates. And the basic message is that it's pretty faithful, close to the reference point. It's essentially building in the harmonic force constants got from the ground state, applying them to the excited state. You can also analyze the Hamiltonian and get from it a set of model parameters. And this shows you the form of this model Hamiltonian. And the picture on the right basically shows how well it works. The thing to compare are the blue curve, the blue and the orange there, which show the difference between the model Hamiltonian and what you would do by fitting potential energy surface. And these are some other potential energy surfaces in green and red there. Okay, let me just finish by acknowledging the people who've done the hard work and have contributed to this. The real workers in this are Marat Sibayev and Yakov Polyak in my group, David Kreplin, Callum Bungie, Thomas Dresselhaus, and Ulia Mordovina, and all those other people mentioned there, and these people who've kindly given us funds. And thank you very much for your attention.
Thank you very much indeed, Peter, for this very interesting talk. And so the presentation is open for discussion. Are there any questions? So if so, please raise a hand. I hope I can. Ah, yeah. So Christian. That's one. Yeah.
Thank you very much, Peter, for this nice presentation. Could you briefly comment on this alternative option to optimize these orbitals through Lagrange multipliers? Would this be just inferior in any respect, or are there also advantages of such a Lagrange multiplier approach rather than this exponential one?
So I guess I can say two things. One is it's what most conventional, in other words, cubic scaling Hartree-Fock programs do. They adopt Lagrange multipliers, and they're of course the orbital energies. And the second thing to say, it was done 50 years ago for MCSCF, but then abandoned. And it's just simpler to do things completely unconstrained. It's just simpler. Constraints are not pretty, as you might remember from the talk yesterday on doing second order density matrix theory. It's just much simpler to do unconstrained.
I guess the same then also applies to the optimization in one part reduced density matrix function theory of the natural spin orbitals then.
Well, there it's different because you can't avoid the constraints. Oh, I see. For density matrix functional theory, yes, the same applies. Yeah.
Okay, thank you.
Are there any further questions? We still have time. Just going through. That doesn't seem to be the case, but actually I have one question myself, and so Christian raised his hand again. But concerning the think it was in towards the very end. So this coupling to the vibrational mode. So have you tested that also for, say, ultra cold molecules? Because there, I think, from the experimental point of view, they have very, very good numbers concerning the vibrational modes of this, say, raw vibronic ground state, and maybe there's some first excited states. And I guess in particular, if you go out towards the dissociation of the molecule, then a very good knowledge of these vibrational modes and the coupling becomes very important.
No, we've not done it. And actually, I think you need to include rotation as well. So the formalism that we set up is targeted towards not very small molecules. So we've essentially gotten rotation. But I mean, you could do the same thing, but we don't have the apparatus to do it.
Okay, thank you. Christian, do you have another question?
Yeah, so just out of curiosity, Peter, did you also consider the application of MCSCF to Bose-Einstein condensates? Or do you know anything about this? What is?
No, what do you mean by that?
So just like instead of fermions, consider bosons, also with a larger one particle Hilbert space, and then the kind of the analog of the single slate determinant or Hartree-Fock ground state would be just like the complete condensate state, all the n bosons in the same one particle state, maybe the lowest one particle state of the harmonic trap, for instance.
So that's a pure
action.
I mean that's a pure nuclear motion problem, right? So I guess one could do that with, I don't know, multiconfigurational time-dependent Hartree or one of those approaches.
The point is, you then also would like to consider, of course, then finite quantum depletion, so which means at the end, not all the n bosons are sitting anymore in a one particle state, and even this one particle state in which most of them are sitting, is kind of to be optimized because the pair interaction between the bosons, of course, changes this from the lowest harmonic trap state, and of course, there are like techniques like Bogoliubov approximation for the regime of very small quantum depletion, which means almost all of the bosons are sitting in the same one particle state. But there's now more and more interest also in experiments to explore the regime of larger quantum depletion, where let's say only 50% of the bosons are occupying a specific one particle state. I mean, I've seen there's some ideas to apply MCSCF to this, but I was just curious whether you know anything about this. And because some of these applications are also then quite often applied to systems of n bosons on two lattice-sides, so just a one particle Hilbert space of two lattice-sides, and this is quite basic, a little bit boring. And some of the point about this, sorry, Peter. So the tricky point about this is, in the context of Bogoliubov theory, the true physical ground state of such a system, you cannot really describe it by just a finite number of excitations to this ground state configuration. You cannot say, I just excite or is two bosons of my macroscopically many bosons to some virtual state, but you need to even macroscopically, you need to consider macroscopically many excitations, and just the probability for those macroscopic excitations just dropping related to the energy, and therefore it's kind of somewhat tricky to apply any kind of CI-inspired approach. And I'm kind of wondering what is kind of a combination of transforming into a quasi-particle picture as it's done in Bogoliubov, and then afterwards applying some type of CI method. And I would say in like some self-consistent CI method, because the one particle state in which all the bosons are at the end sitting, or many of them, has also been optimized.
Yeah, I guess I haven't thought about it, but I understand the point, because you really would need to optimize the one particle states in the presence of a correlation. Yeah.
Okay, so thank you for this lively discussion, and I hope Christian and Peter can continue maybe at one of the discussion tables. And so with this, I would like to move on. And I very much welcome Christian Ochsenfeld from the Ludwig-Maximilian University.